Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about another method to determine the gas phase diffusion coefficient with the help of experiment. So in the previous lecture we have discussed about the gas phase diffusion coefficient. We determine the gas phase coefficient with the help of experiment, and we use the twin bulb method to determine the gas phase coefficient. Now in this method we will use the Stefan tube experiment to determine the gas phase coefficient. So we will determine the gas phase coefficient with the help of Stefan tube. So it is the second method which is used to determine the gas phase coefficient. So the gas phase diffusion coefficient, DAB. So this is the Stefan tube. This one is a Stefan tube. This figure is Stefan tube. The Stefan tube consists of a vertical tube. This is a vertical tube. This is a vertical tube. In which some volatile liquid, which is component A. So some volatile liquid is present in this Stefan tube. This is the volatile liquid. The volatile liquid is denoted by component A, and the gas is denoted by component B. So a volatile component is present in this vertical tube. There is another tube which is the horizontal tube. So this is another tube which is the horizontal tube. So this is the vertical tube, and on the top of vertical tube there is another tube which is the horizontal tube. And in the horizontal tube the gas is flowing. So we flow a gas B through the horizontal tube with the help of some driving force. This driving force can be compressor, it can be fan. So the gas B is transferring from left side to right side in the horizontal tube, and in the vertical tube up to some height, up to this height, there is a volatile liquid which is component A. So when the B is passing through the horizontal tube, the A will evaporate, and A will transfer from liquid state to vapor state, and it will mix with component B. So in this place there will be two components, one will be component B and one will be component A. So here A plus B component is present. So there is two components present in this place. So there is two component A and component B present in this place. So this is component A, which is volatile liquid. The gas B is the component B, which is gas. When the B gas passes through the horizontal tube, is the A is volatile component, so the vapor of A will form in this place. So the vapor of A will diffuse through this vertical tube, and finally it will mix. The A will mix with B. So A will mix with component B, and mixture of A and B will pass out from the horizontal tube to the surrounding air. Now this A is volatile liquid. The vapor pressure of liquid A at the vapor liquid interface is PA1. So the vapor pressure of liquid A, this is the liquid A, this is the vapor liquid interface. This is the below is liquid phase and above it is vapor of component A. So if this is the interface, this dot line is the interface, vapor liquid interface. So the vapor pressure of component A at the interface is called PA1, vapor pressure of liquid A. So at this place, at this interface, the component A will transfer from liquid phase to the vapor phase, and this dz is change in the height of the vertical tube. So change in the height of volatile liquid which are present in this vertical tube. So this dz shows us the change in height of the volatile liquid in the vertical tube, dz, and z is the on the vertical side. So this z shows the distance between the distance between the wafer liquid interface. This delta Z shows the distance between the horizontal tube, and the wafer liquid interface. So this Z shows the distance between the horizontal tube and the wafer liquid interface. Similarly, the dz shows the change in the height of the volatile liquid in the vertical tube, and the cross-sectional area of this vertical tube is denoted by A. So suppose this is the cross-sectional area. This cross-sectional area of the vertical tube will be denoted by A. So this will be the inner cross-sectional area of this vertical tube will be denoted by small a. So, and this is the component B. So this is called the Stefan tube. This Stefan tube is used to determine the gas phase diffusion coefficient with the help of experiment. So we will use this tube to determine the gas phase coefficient, which is the DAB. Now there is some assumption to determine the gas phase diffusion coefficient with the help of Stefan tube. The first assumption is the diffusion of component A through component non-diffusing component B will be occur. So there will be a diffusion of component A through non-diffusing component B. So component A will diffusing through component B, but component B will not diffusing through the component A. So component only and only component A will transfer and it will diffusing in the component B, but the component B will not diffusing in the component A. So again the component A is converted into wafer. The A is converted into wafer. It will diffusing. This is component A. Suppose this is component B. So the component A will diffusing. Through the component B, but the component B, which is this component will not diffusing through the component A, which is present in the liquid phase here, This is component A. So component B will not diffusing through this component A. This is the assumption. And diffusing of component A through if you don't know diffusing of component A through non-diffusing component B, you must watch my lecture about diffusing of component A through non-diffusing component B. Its video will be present in the description. You can watch it to fully understand the concept of diffusing of component A through non-diffusing component B. Similarly, the second assumption is pseudo-steady state assumption. So when the liquid level slightly drop in the tube, a new equilibrium will reach simultaneously. So when the A evaporated from the vertical tube, then the liquid level in the vertical tube will slightly decrease. As the liquid level in the vertical tube slightly decrease, then at the same time a new equilibrium will reach. So when the liquid level slightly drop in the tube, a new equilibrium will reach soon or simultaneously. So when the liquid level slightly decrease in the tube, suppose this is the tube, when the liquid level, suppose at first it's the start of experiment, the liquid level was up to this point. Now after a certain time the liquid level decrease and the liquid level come to this position. So when the liquid level decrease in this vertical tube, at the same time a new equilibrium will reach. So this is the steady state assumption. We assume that diffusing of component A through non-diffusing component B is at steady state. So this is the steady state assumption. Now we know that the flux of component A through distance Z is denoted by the flux of component A through distance Z is denoted by NA. So the flux of component A through the distance Z is denoted by NA. The flux of component A through distance Z is denoted by NA. So the NA is equal to DAB into P. So the flux of component A is denoted by the flux of component A, this one. The flux of component A through distance Z is denoted by Na, which is DABP into PA1 minus PA2 divided by RTZ PBM. This PBM shows the log mean, the log mean pressure, the log mean. This is shows the log mean partial pressure of component B. So log mean partial pressure of component B, PBM. Log mean partial pressure of component B. So this is for, if you don't know, please watch my video about diffusing of component A through non-diffusing component B. So you will fully understand this log mean or partial pressure of component B. So usually when gas is passing through a horizontal or vertical cylindrical tube, then in that case we use the log mean partial pressure of component A or partial pressure of, or log mean partial pressure of component A or B. So in this case these are the assumption. The flux of component A through the distance Z is denoted by NA. So the flux of component A through this distance. So the flux of component A through this distance Z. This distance Z is denoted by NA. And the equation for it is DABP PA1 minus PA2. So this PA1 is, what is the PA1? The PA1 is this, the vapor pressure of liquid A, and PA2 is the partial pressure of component A at the top, at this position. The partial pressure of component A at the top of the vertical tube. So at this position the partial pressure of component A. So at this position the mole of component B will be very high. At this position there will be large amount of component B, but very small amount of component A will be also small. So we will ignore the partial pressure of component A at this position. So PA2 is approximately or negligible, which is equal to 0 in this case. So this PA1 is the vapor pressure of component A at the vapor liquid interface, and PA2 is the partial pressure of component A at the horizontal tube, which is negligible, or we can say that it is 0. And this is the log mean partial pressure of component B. This is the universal gas constant, this is the constant temperature, this is the Z through which diffusion is occurring, and N is the flux of component A in the Z direction. So this is equation number 1. Now this is equation number 2. How can we derive this equation number 2? So we will come to it. At this time we will not discuss it, but after discussing the material balance we will come to this equation. So first of all we should discuss the material balance equation, then after that we will come to this equation. So what is the material balance equation? What is the general material balance equation? The general material balance equation shows that input minus output plus generation minus consumption is equal to accumulation. So input of component A minus output of component A plus generation of component A minus consumption of component A is equal to accumulation of component A. So we assume that it is a steady state process, so accumulation term is 0. As there is no input to this tube, so the input is 0. The consumption, there is no consuming of A, so this is also 0. The generation, the A is generated from the liquid. The vapor of A is generating from the liquid of A. So this is the vapor of A, vapor of component A, and this is the liquid of component A. So the vapor of component A is generated from the liquid component A. So this is the liquid component A, and this is the vapor of component A. So the vapor of component A is generated from the liquid component A at the interface. So A is generated, so generation, and as A generated at the interface, at the same time A is coming out or A leaving the interface. So the rate at which the vapor of component A generated at this interface will be equal to the rate at which the vapor of component A leaving this interface. So is the vapor of component A generated from the liquid component A at this interface, then at the same time the generated vapor of component A will be leave this interface. So the generated vapor of component A will be equal to the outgoing vapor of component A. So is the A generated, so the generation rate will be equal to the outlet rate. So the amount of A which generated, the amount of vapor of component A which generated at this interface will be equal to the amount of vapor of component A which leaving this interface. So the generation rate is equal to the leaving rate, or the generation rate is equal to the output rate. So the generation of A at the interface is equal to outgoing or leaving of A from the interface. So this is equation number 1. Now the mole of A going out or leaving interface is denoted by mole per unit time. So a mole of A going out or leaving the interface is denoted by mole per unit time, or A into Na. So the mole of A leaving the interface is denoted by A. This is the inner cross-sectional area of the vertical tube, as we already discussed. This is the Na, the flux of component A in the Z direction in the vertical tube. So the mole of A going out, so the A into Na, the A into Na, the unit of this A is meter square area, and this is the molar flux. So mole per unit area per unit time. So area cancel with area, mole per unit time. This is the molar flow rate. So the molar flow rate of A going out or leaving the interface is denoted by mole per unit time. So the interface, the mole of A which leaving the interface is denoted by A into Na. So let's see the mole of component A which leaving the interface. This one, the mole of A which leaving the interface. This is the interface, and the mole of A which leaving this interface, mole of A which leaving the interface is denoted by A, which is the cross-sectional area of this tube, and the molar flux of component A, Na, and this Na is denoted by this one, this Na, denoted by this Na. So mole of component A is denoted by this one. Now the mole of A generated at the interface is the generation rate of mole of A is equal to change in mole of A per unit change in time. So the generation rate is denoted by dNA divided by T, where Na is the mole of component A which generated at the interface. So the mole of A which generated at the interface, the mole of A which generated at the interface will be equal to the mole of A which generated at the interface will be equal to the mole of A which generated at this interface. This is the interface, and the generation rate will be equal to dNA change in mole of and the change in time. So this is generation rate. The generation rate is equal to the leaving rate, this one. So these two are equal. Now generation rate is equal to the leaving rate. This is the generation rate. The generation rate of mole of A is equal to dNA divided by T, where Na, this Na is the mole of A, mole of component A. So change in mole of component divided by change in time is the generation rate of component A. Now we know that the generation rate is equal to dNA divided by dt. We know that mole is equal to mass of component A divided by molar mass of component A is equal to mole of component A from the definition of mole. So we also know that, so in place of mole we will So in place of mole we will write mass divided by molar mass. So we also know that the mass can be converted into volume and density by this relation. So mass density is equal to mass of A divided by volume of A. So volume of A into density of A is equal to mass of A. So in place of mass we will write density into volume of A. If the density of a liquid is constant, then it will come out from the differential. Density is constant, it will come out from the differential. So this is the density of component A into change in volume divided by molecular weight of component A into change in time. So this volume, again this volume is nothing but it is the volume of liquid in the vertical tube. So the volume of component A in the vertical tube, suppose this is the volume of component A in the vertical tube, this vertical tube. So this one is the cross-sectional area, this A. This one is the cross-sectional area of the vertical tube, like this one. Cross-sectional area of the vertical tube, and this one, this one the dz, change in the height. So height multiplied by cross-sectional area is nothing but the volume. So in place of volume we will write, area into change in height, which is nothing but volume of component A. So the area is constant, it come out from differential, and the change in the height will be not constant. So the change in height with change in time, and this is the MA. So putting equation B and C in equation number A, equation B and C, this is equation number B, this one equation number C, and equation number B. So this is equation number B, this one is equation number B, which is the leaving rate. So the leaving rate is equal to A into NA, and this is the generation rate. The rate of generation of component A is denoted by this equation number C. So put equation B and C in equation number A. So the equation number A is nothing but it is this equation number A, which is input minus output plus generation minus consumption is equal to accumulation, and the final equation number A was this one, generation is equal to output. So this is the generation and this is the output. Generation of component A at the interface is equal to the rate of leaving of component A from the interface. So the generation rate is equal to this one. This is the generation rate of component A, this is the leaving rate of component A. So from equation number 1, the rate of leaving of component A, is equal to this, the flux of component A which leave the liquid vapor interface is denoted by DAB PA1 minus PA2 divided by R2Z PBM into P. This was from equation number 1. So put equation number 1 in this equation, suppose this equation number Z. So put equation number 1 in equation number Z. So we will write rho A, density of component A divided by molecular mass and to the area of the vertical tube, dz by dt is equal to area, yes, and to NA, and NA is denoted by this one. So this one is, we will put this one in this place. So this is the generation, the rate of generation of component A at the liquid vapor interface is equal to the rate of leaving of component A from the interface. So these are the two equations. Now so this is the equation number 2. Now we know the flux of component A through the distance Z. The flux of component A through the distance Z is equal to NA. We have already discussed. This is equation number 1, and this was the rate of generation of component A at the interface. This is the rate of generation. So the rate of generation, now this one shows the rate of generation of component A at the interface is equal to the rate at which component A leaving the liquid vapor interface is denoted by this one. So the generation rate is equal to the living rate. So this from this equation, so this equation number D, this equation number D is nothing but it is the our equation number 2. So we already said that we will come to equation number 2. So the equation number 1 was this, but the equation number 2 was obtained by material balance equation. The generation of component A at the interface is equal to the rate at which component A leaving the interface. So this was our final expression. So this was our final expression for the component A. So this was the now this is our final equation. Now Stefan method and so the equation number 2, this was equation number 2. This was equation number 2. Now this was equation number 2 which we derived from material balance equation. This equation number 2. Now we rearrange this equation number 2. This is again the equation number 2. Now by separation of variable method, we will separate the z will come to this side and the type. So only and only with the passage of time the height of the volatile component will decreases with the passage of time. So the height of component A will changes with the passage of time. So the time, as time changes, the z will be changes. And the other are constant component. This one is constant, this is constant, this is constant, this is constant, constant, this is constant, these two are also constant, this constant, these are all constant. So we will, this z will come to this side. So z into dz is equal to ma into a dab p pa1 minus pa2 divided by rt pbm rho, and this is the change in time. We will take the integral from z0 to z. When z is equal to z0, when t is equal to 0, when t is equal to 0, when time is equal to 0, z will be equal to z0. When time is equal to some other time, then z will be equal to z. So these are the limits. So when t is equal to 0, the height, the z will be z0. So after when t is equal to t, then z will be equal to z. So after taking the integration, we will take the integral. This one is z squared divided by 2. This is the limit z0 up to z. This is from when t is equal to 0, z will be equal to z0. When t is equal to t, the z will be equal to z. Height will be equal to z. And these are all other constant term. So applying the limit z square minus z0 square divided by 2 into molecular weight of component A, diffusivity of component A in the component B, total pressure, and PA1 at the liquid vapor interface, the vapor pressure of component A at the vapor liquid interface, the partial pressure of component A in the horizontal tube, which is usually 0. We ignore this component. And this is the final temperature, the final time. This T can be equal to Tf or it can be equal to T. So this is the density of component A. This is the log mean partial pressure. This is the log mean partial pressure of component B. This is the R, universal gas constant. This is the temperature, absolute temperature. Now rearrange this equation, simplify this equation in order to get DAB. So DAB, when we obtain DAB, these term will come to this side, and this term and these all term will also come. The all term will come to the denominator. So we will obtain this DAB. So after simplification, the DAB is equal to, this is after simplification, the DAB is equal to z square minus z0 square divided by 2 RT PBM density of component A, molecular weight of component A, total pressure PA1 minus PA2 into time. So this is the so from this equation we will obtain the gas phase diffusion of component A. So from this expression we will get the diffusion for the gas phase diffusion coefficient with the help of Stefan experiment. From this equation we can get the diffusivity of component A through the component B with the help of experiment, which is called the Stefan experiment. So this these limit can also be applied at this position. We can also apply the limit like this one. We can put the limit like we can put the limit here. We can put the limit we can put limit in our integration equation like this is when t is equal to 0 at the beginning, the z is equal to z0. So when t is equal to 0 at the beginning, the height of the liquid in the vertical tube is equal to at the beginning this z is equal to this z. The distance from the liquid vapor interface to the horizontal tube will be equal to z, which is equal to z will be equal to z0. When time is equal to 0 at the beginning this distance is equal to z0. After a certain time, when t is equal to tf or time is equal to t, then this z, the z will be equal to z. So after a certain time, a new height will be obtained. So after a certain time, a height will decrease. The height will increase from the top. So a new height will be obtained. This blue one height will be obtained. The blue one height will be obtained. Which will be equal to z. So the height from the top will increase, but the liquid height in this tube will decrease. So when t is equal to tf or t is equal to t, when t is equal to tf or t is equal to some later time, then this height, this z will be equal to this z. So this is the limit. So from this we will obtain the diffusivity of component A through the component B. Thank you very much for your attention. If you are new to the channel,